now let's get started. So the last time, as I mentioned last time, so we're going to move on to a bit more, talk about global structure of space-time using Raychaudhuri equation and so on. Before that, I'm going to introduce a notion called Killing horizon to describe the nature of horizon and also surface gravity and so on. So we already know that the event horizon, and also so we somehow encounter so-called surface gravity at the gravity. In the case of curve, which is kappa, we call it, and also so we encounter singularity in black hole, also Big Bang. And those are can be understood a bit more how to say general manners. So that's the first we are going to talk about how to characterize the event horizon and surface gravity first. Okay, so first, so this is today's lectures. So when you write down the vector, people just write down whatever. I don't know. I mean a BA or B mu, whatever you call it. B mu is that it's called tangent vector or tangent vector like this way, which is something like if it is time-like in space-time case, if you write down the line. Or whatever. So the trajectory of the observer, whatever you call it, which I call it the gamma of t. In the space-time, you have a local coordinate x mu, gamma of t, and if you take divided by dt, you get a speed. I call it b mu at the point p. So therefore, so if you just take a time derivative, you get the b mu. B mu is like this way. So, okay. Those are the b mu. So there's a tangent vector of this curve, this curve, whatever, the point. So these are like a b mu of t and b mu of t prime. This is t prime and t and so on. So those are definition of tangent vector. I'm not going to go into the detail of this kind of like the differential geometric object, because rather I want to discuss the physics using that one. So therefore, so for instance, if you have the let's see, if you have like this way, so so this kind of curve will give you so-called one parameter diffeomorphism. So if you have a space-time, like a space surface like this way, sigma, if you take a time translation, so the time translation of this curve, so you just push to this sigma to sigma prime, okay? So that will give you something called diffeomorphism flow of the this curve, this like a congruence of curve flow, which is I call it h of whatever h flow. Diffeomorphism. And then in terms of this flow, this vector can be, for instance, this vector can be push forward to this h star of b mu. You can just push forward this vector to this vector. And you can compare between this vector. Okay, let's write down the push forward one like this way. Push forward h star of b mu, and you can compare the genuine tangent vector. So the difference between them is called Lie derivative. So Lie derivative of the whatever whatever call it. So b mu or xi mu, whatever. Xi mu. Okay, so my b mu of b is equal to limit s goes to 0 when bp minus h s star bp divided by s. So that's the so that's a differential derivative. In any case, so if you have a flow, so if this kind of flow, which is generated by b mu, so those are vector field b mu. So those are vector field b mu. And there is a vector, whatever I call it, vector b. I call it b. You can push forward this vector around here. There's another vector, whatever vector field you have. So anyway, so I don't know. So this kind of vector field, if you can have capital B, or let's see, these are vector field at a different point, but you can push forward this vector by this flow, by this flow. That it can be like this way. That is called the push forward of time s of b. Okay, and then you can take a difference between them. And if you take s goes to s is whatever affine time between these two points. Okay, these 2 points. And if you take s goes to 0 limit, you can take so-called Lie derivative. Okay. For instance, if you have the whatever x, two vector field x mu and y mu, so leave a derivative of x, and then and the y is in fact the commutator of the x and the y, which is something like a x mu, partial mu, y mu, so then minus y mu, x mu. Okay. So that's also, it's called Lie derivative. Okay, and then similarly, so we can just do the opposite process for differential form. Differential form is instead of like a push forward, we have to pull back somehow. So these it's called push forward. Anyway, push forward, and for vector field, so the vector field. Instead of the vector field, you can consider differential form. Differential form is the indices is downward because you just need to maybe mu. You need to pair with dx mu, so the indices are omega mu. I mean, gravity people just write that, just omit this one, dx mu, and just write down the lower indices like this one. For vector field, upper indices. For the differential form, you have a lower indices. For differential form, so you can do the pullback. So here, you have pullback. So the same diagram, whatever. So you have a flow of the vector field B, whatever B, and so on. So one can have the omega. So if you have omega, so B mu, and this from this point omega mu, and then you have also the whatever. Omega mu is something like it's not vector, so I don't want to write that like this way. But anyway, omega mu, and you have at even this point you can have the omega mu of P. And omega mu of gamma s of p, like this way. And you can just pull back this one into here. Okay. So pull back is just instead of push forward, you just go backwards in the affine time. So in the backwards in the affine time. So the derivative of the v of whatever omega is equal to limit of s goes to 0, omega whatever, whatever, minus h s pullback of omega, and take s equals to 0. So it's just a opposite procedure, because I mean, b mu and the omega mu just can take the contraction. Therefore, if you push for this one, you have to pull back this one. So it's just some like it becomes opposite process for differential form. Anyway, so like this. And in particular, so the metric G mu nu is a low end sense, which is paired with dx mu, with dx nu. It's a symmetric one. It's a differential form. And then if you take the derivative of this G mu nu, G, the metric, you can just have like this way. I'm not going to go into detail for this derivation. It's not so difficult, but I'm not going to go into the detail. So just let's accept that. So it becomes like this. This is the ordinary covariant derivative. Derivation is written appendix on my paper. Not my paper, my lecture note. Let's accept that. So this is a case, and if this one C satisfied, C is the that preserve metric. So C mu, then it's called a definition killing vector. Okay, that's called killing vector. Which means that if you, another flow, so you have a flow by C, whatever. So now I don't know why I just changed the notation for V to C, but I hope it's okay. And then, so if you just pull back metric here, so the point metric G, and pull back under the flow like here. So for instance, if you just do the pullback is just a go backwards in a fine time, and just look at the induced metric on here. If the induced metric is the same as original metric, the metric is preserved. Okay, and that is equivalent to the showing that this L C of Z is equal to 0, which is del mu C nu plus C nu is equal to 0. Okay. If this is satisfied, it's called killing vector. So yeah. Anyway, so induced metric by this diffeomorphism, by pullback of diffeomorphism, is the same as original metric. So this is called killing vector. That's the case. Okay, example. It's very easy to construct example of killing vectors. So instead of apart from the different so GR, so for instance one can consider R2, and if you consider whatever R2 in the standard metric, dx squared plus dy squared, standard metric. So what is a killing vector? Can you come up with killing vector? For R2. Huh? D phi. Like this way, you mean? Yes. Yeah. So this is okay. So for instance, it's a rotation. So he mentioned rotation. I mean, this is a rotation. Rotation does not change the metrics. That's true. Okay. So this is the dd phi. Or dd theta, whatever you call it. dd theta. I mean, theta is like this way. Or just a constant translation. so ddx, or so dd delta y. So that does not also change the metric. That's also the case. In the case of S2, with standard metric, ds square is d theta square plus sine square theta d phi square. So S2, so for instance, del phi does not change the, is a killing them. So it's just a rotation around the z-axis. Rotation around z-axis will produce a vector field, something like this one. Vector field. Anyway, it's not differential geometry course. I'm going to omit the details. Those are Killing vectors. Because I mean the flow generated by this vector field is indeed isometry. So which means so isometry. So this means that the flow generated by C mu is an isometry. Isometry means that the isometry. It means it does not change the metric. Diffeomorphism and isometry. A diffeomorphism which does not change. And the key observation is that for instance, so locally, so any vector field C mu can take any vector field can find local coordinate whatever x mu such that the C mu is something like this one. But anyway, maybe the best way to write down is like this way. Like this way. So that the C mu is something like 1, 0, 0, something like this. Locally. Also, the important thing is only locally, not globally. Okay. So in that case, this lead derivative of C of g mu nu is just g divided by x1. It becomes like this. G mu nu. Like this one. Okay. So therefore, this means that locally, if you locally metric is independent of x1, then the delta x1 is the killing vector. So therefore, from this perspective, it's easy to show that the Schwarzschild black hole, the metric is something like a ds square minus 1 minus 2m over r dt square plus this one inverse dr square plus whatever d theta square plus r square d omega 2 square. Okay, so that's the case. So the metric, so locally metric component is independent of time, right? Independent of time. So therefore, this one is killing vector. That's of course true, but because it's static means that if you do the time translation, the static means that if you do the time translation, physics does not change. Time translation is generated by this delta t. So the flow of delta t is a time translation. Another thing is the del phi. Del phi, because I mean it's independent. The metric is independent of phi, so it's a of course rotational symmetric because it's a spherical. So not only del phi, in fact, any rotation. So is also Killing vector. But moreover, so not only, so delta phi is the rotation on the z-axis, roughly speaking. But not only rotation on z-axis, any axis is okay. That will give you flow. But it's a hard, I mean, it's not straightforward to write down like this way. It's a bit more complicated combination, combination. So anyway, so if you write down a Cartesian coordinate, it's something like whatever. Cartesian coordinate, this is the rotation. This is the rotation in z-axis, but if you just write down like for instance y del del z minus z del del y, this is a rotation along x-axis, rotation along x-axis in Cartesian coordinate, and so on. So those are Killing vector even for Schwarzschild. Okay. Okay. And even car. So car, I'm not gonna write down the metric again, but it's independent of time. Okay, it's independent of time, and also it's independent of phi. It's independent of phi. So therefore, those are Killing vector. Of the curve metric. So I'm not going to write down a metric again. It's meaningless. But the important thing is that this guy, so Schwarzschild is called, what was it? Schwarzschild is this static and then axisymmetric. But here, stationary. And then axisymmetric. Okay. So.
Why did you write axisymmetric in Schwarzschild?
Huh?
Axisymmetric in Schwarzschild. It's spherical symmetric, right?
It's yeah, but it's also axisymmetric, right? So yes, stationary. That's true. Spherical. Yeah, not only is axisymmetric. Oh, okay. Not only. Okay. Maybe okay. So more general, spherical symmetric. Spherically symmetric. Okay, so the definition is that the stationary is that a static. Means that this is Killing vector. And what we have is the T zero symmetry like this way. But stationary is this only this one, and not this one. We don't have this one. We don't have this. So since the curve metric, we have a d phi dt term with some g phi t, right? So ds square contain this cross term in the metric. So when you take t goes to minus t, this you get the minus sign. Okay, you get the minus sign. So therefore, the metric is not invariant. So this is invariant. Okay, it's not invariant under this time reversal. Time reversal. It's called time reversal. So the curve does not have this symmetry because of this cross term. Okay, cross term. So that's why it's called stationary. And then, what was that? Axisymmetric is axisymmetry is that delta phi. Delta phi is the Killing vector. Delta phi is a Killing vector. I mean, there is a more general definition. If there is a more general definition, if there is some Killing vector xc that satisfies asymptotic xc squared is equal to minus 1, which means timeline, then it's called, and they satisfy, then it's called stationary, more generally. But we can take this c as a delta t, actually delta t, so it's okay. The same thing here. So it's more like a spatial closed. The flow is a spatial closed curve. Then you can make it more general, but I'm not gonna go into detail. Anyway, so that's the case. Okay. So what is important for this Killing vector? Why do I talk about this Killing vector? Is the first of all, this will play the role of conservation. Because we already knew, actually, we already used this back that so both Schwarzschild and then the curve del t and the del phi are Killing vectors. And this is the so-called conservation rule of the epsilon and L. So that corresponds to epsilon and L. So we already knew. So let's derive a bit more formally for this one. So in both Schwarzschild and so we know that the epsilon is something like whatever. dt d tau with appropriately normalized whatever. dt d tau, some appropriately normalized one. This one is anyway. Let's not go into that. I'm going to derive that. Anyway, so let's derive that. So suppose I is equal to something like whatever minus g mu nu. X dot nu d tau. Tau is the proper time for massive particle. Tau is some affine parameter for the massless particle. So this is the action. And take the point. So if you have a Killing vector field, x mu plus alpha xc mu. Okay, xc mu. So this is a Killing vector. Let's see how it behaves like. So let's see. Maybe I will use this. So variation of this action can be understood as follows. So delta I is equal to minus alpha e d tau, and the g mu nu k dot mu x dot nu plus g mu nu x dot mu k dot not k xc, sorry, xc sigma plus g mu nu sigma x dot mu no. So this is the c sigma. Okay, so that's the case. So x is the x dot is the variation x dot is the c dot, and also the variation metric. A variation metric is the derivative. So this is derivative of the sigma and xc sigma. Okay, xc sigma, and then we can just do the manipulation. For instance, c dot mu is indeed equal to so this is dx mu d tau, right? But we can do this kind of a trick, do the chain rule. So therefore, this is x dot nu c mu dot nu. Okay. So like this way, and plug that one into here, and what you get. So what you get is minus alpha d tau, and then g mu nu x dot sigma x dot nu c sigma dot mu plus g mu sigma k x dot mu x dot sigma like this way. And the last term is the same. G mu nu dot sigma x dot mu x dot nu and the k sigma. Okay. Like this way. So that's the manipulation. And if you use sorry. Somehow I changed my election of this K somehow. And if you manipulate this one, what you get is that if you change the indices very nicely and so on, what you get is as follows: minus alpha d tau x dot mu x dot nu, and then what you get is the del mu c nu plus del nu c mu. Okay. And since we assume that c is a Killing vector, this is equal to 0. Okay. So therefore, this the action of this massive particle or massless particle, whichever, is invariant under this variation with respect to Killing vector. So therefore, from here one can see that the conservation rule. So the Q is equal to C mu, P mu is conserved. Quantity. So therefore, yeah, so this guy is equal to in fact P whatever. PT, and this is equal to P5 or something like that. Okay. So where P is defined by del L del x dot mu, which is G mu nu, from this action is something like an x dot mu. So this is the conserved quantity. I mean this one, it's easy to show by using Euler-Lagrange equation. Okay, so under the variation, so we know that if the delta x mu is equal to this Killing vector, then the action is equal to del I is equal to 0. Okay, so this means that the del L del x mu and del x mu plus del L del x dot mu del x dot mu equal to 0. Okay, that's what we have. Okay, and the Euler-Lagrange equation told us that Euler-Lagrange equation, this means that the minus no, it's not dd tau x dot mu del x mu plus del L del x dot mu is del x mu dot mu equal to 0. Okay, so here to here, so you have to use so this part is equal to this one by Euler-Lagrange equation. Okay, Euler-Lagrange equation. And use this definition of the momentum. If you use plug this one in the momentum, okay, then this is equal to p dot p mu dot, and this is c mu, and this is p mu, and this is c dot mu equal to 0. Okay, and this is equal to d tau, d tau, and p mu and c mu. Okay. So therefore, this the inner product of p mu and the Killing vector is invariant under this proper time. So therefore, it's a conserved quantity along geodesics. Maybe along geodesics. Along geodesics. Okay. Okay, so that's the case. Fine. Any question at this moment? Okay. So in Schwarzschild, oh, there's no 1/2, sorry. Yeah, it's true. There's no 1/2. So in Schwarzschild case, this epsilon is defined as something like a pt, which is something like a -1 minus 2 m over r dt d tau. Okay, this is conserved quantity, and then no, I think it's just pt. Sorry, pt is minus epsilon. And L in the case of Schwarzschild is just p phi, which is r squared sine squared theta d phi d tau. So these are the case of Schwarzschild. So these are the conserved quantity along the geodesic, and we use this one for many times. Okay. Any question at this moment? So therefore, for Killing vector, one can define. So this is a point of the one point of Killing vector is a conserved quantity along geodesic. Okay. Another thing is that so one can just so-called define Killing horizon for no hypersurface. So hypersurface is whatever. So from now, so first important thing for Killing vector is the conserved quantity. Another thing is so-called Killing vector, Killing horizon. Okay, Killing horizon, which is the somehow to define that one has to so it's called some new hypersurface. With certain property. Yeah, with certain property. With the killing vector, no killing vector. What is normal to where? Okay, so that's the definition. So to define that, so we have to first understand what's a no hypersurface. So and hypersurface. What is a hypersurface? Hypersurface is that if you have a vector, it's a very simple thing. I mean, if you have a vector field, something like this one, so n mu, we just define the normal surface. I call it the sigma. Hypersurface can be defined given a vector field. You just define some like the surface which is normal to this in this vector field. It's a normal. So to define that, we define so-called the function. So the function on the space-time. So I'm going to talk about only like a GR case. So for instance, the locally everything like R1, 3 or whatever. The curved space-time is locally like this way, but anyway. So you consider the function S of x is a function, smooth function. On the space-time. Space-time can be curved. It's a curved one, and then n mu is equal to f of x is g mu. It's called gradient vector field. So this is called gradient vector field. S. Okay. So you just define the vector, gradient vector field n of mu. Then this sigma, the hypersurface which is normal to n mu can be is in fact S of S is a constant surface. So S is constant surface is normal to this n mu. N mu is this gradient flow. So this is called hypersurface. I mean, it's the simplest example one can just consider is that anyway. Okay, it's a very simple example. One can just f of x is some kind of normalization, some kind of function. F of x will be used to normalize, and the square is equal to usually like this way. In the case of the space-like or time-like surface, if it is time-like, so if it is time-like, then for instance, if you consider torus, so if you have a torus, the function s is the kind of like a height function. So the s of x is something like you just consider that this point is just like this way. It's called height function. It's kind of like height function. So S of x, the hypersurface constant hypersurface is something like this one. Okay. Constant hypersurface like this way. And then of course gradient flow is something like gradient flow, and is something like I don't know which one is the best way. Yeah, something like this way. I mean, anyway, it's hard to. Anyways, those are the end vector. It's a gradient flow of this height function. And there's a so-called critical point around here. Around the critical point, it's no longer hypersurface is no longer manifold. Anyway, so those issue is not important in this GR. In math, it's very important because I mean it's bifurcate around here. Okay, it's a bifurcate, so it's no longer manifold. So it's anyway. Let's not go into the details. So if there's a full critical point in this gradient vector field, but anyway, so let's not go into the details. So, but that's one like a very like how to say intuitive way of understanding what is. But in GR, so the space-time is it's not the how to say Euclidean signature. Okay. So sigma is space-like. So this hypersurface space-like if the and mu is time-like, of course. So as you can see, so and mu is like it's really time-like. It's time-like. Sigma is space-like because also it's a sigma is orthogonal to the normal vector. Okay. Then the sigma is time-like if the mu is the space-like. That's also very natural because if n mu is space-like, the of course there's a like a time direction will be included in the sigma. Fx is normalized such a way that the n square is equal to -1 in this case. N square is a +1 in this case. Okay. For fx is just normalization function of this gradient vector field. Okay, and then the question is that what's called a sigma is called null when n is null. So this is definitely n squared is equal to 0. Okay, so that's the case. So this is called null hypersurface. Okay. Okay. So example. So example is the so in Minkowski. Example Minkowski. So n is equal to 1, 0, 0, 0. Okay, so it's a time-like, and then the hypersurface sigma is the t is equal to constant surface. Okay, first of all, s of x is x0. Okay. So this is 0, 1, 2, 3 coordinate. Okay. So s of the function is this one. So therefore, the hypersurface is the x0 is constant surface. Okay. So therefore, this is exactly what's really happening. So if this is the x0 direction. Okay. Okay, and then in this metric is something like h mu is equal to g mu nu plus n mu, and which is, so this one is the diagonal now of the minus 1, 1, 1, 1, right? And this guy is something like diagonal 1, 0, 0, 0. So therefore, if you add them out, you get the diagonal 0, 1, 1, 1. Okay, which is a space metric on this one, on sigma. Okay, it's a very simple example. And then, of course, you can just consider that here is the time-like hypersurface is the n mu is something like 0, 1, 0, 0. Okay, and then S of x is x1. Okay, x1. And then, so the sigma is the x1 constant surface, like this way. And then h mu nu. Like this way. Then if you do the computation, this is minus 1, 0, 1, 1. So this is an induced metric on the hypersurface. This is super easy. Okay, now let's move on to new hypersurface. Okay. So new hypersurface is the, in fact, so n mu is the null, so that the n square is equal to 0, and the sigma is the orthogonal to n mu. But this means that n mu is tangent to sigma. Okay. Do you understand what it means? Okay. Orthogonal to n mu is that t mu n mu is equal to 0. So where t mu is a tangent to sigma, right? Do you understand what I mean? Orthogonal means that it has to be normal, right? Like this way. T and n, it has to be tangent. So orthogonal means that always the inner product is 0. So that's the definition. However, since that the n is the null, so therefore we know that the n mu is equal to 0. So therefore n itself is tangent to sigma. So this means that the whatever. So if you have a null vector, whatever. So the surface is really tangent to n itself. That's the only way to define.
What you mean? It is orthogonal and tangent
Yeah.
at the same time?
Yeah, at the same time. So
How do you imagine it? How it sounds like it can be orthogonal?
so normal means the product is equal to 0. But in the case of null, so it's itself, the normal vector itself is the inner product is 0. So therefore it has to be tangent.
How you imagine it? Let's imagine space, solution like that.
You have to throw away the notion. you have to solve the notion of the Euclidean orthogonality. So we know of the Lorentz boost. If you do the so if you consider the just time and the x is like this way, and the light cone is something like whatever. Light cone is something like this way, and this one. Oh, sorry. Like this way. But if you do the Lorentz boost, it becomes the time is something, t prime is something like this one, right? And x prime, the orthogonal to t prime, x prime is something like this one, right? Okay. And if you do the really like, if you go to the speed of light, t and x prime is just the coincide. So therefore, the tangent becomes normal too. That's the intuition. So you have to throw away the notion, the intuition of the Euclidean signature. The orthogonality is, in Minkowski is different from orthogonality in Euclidean signature. Anyway. So moreover, no hypersurface segment. I don't know why I use L here. Why? Anyway, so no hypersurface sigma normal vector and mu how to say the gives geodesics becomes integral curve of normal vector of n mu becomes the geodesic. Geodesics. I think my handwriting is horrible now. Geodesics. So integral curve is that literally something like if you have an mu, integral curve is really like this way. The curve is something like this way. Along this. There's a different point. It's integral curve is something like this. So this becomes the null geodesic. Normal vector of this. So this is a claim. It's okay, let's prove that. Okay. So suppose and mu is again something like a f of x g mu nu del nu s. So that's the case, and we satisfy and square is equal to 0. So this is the new how you define a new hypersurface, and the s is equal to constant is in fact is equal to sigma. Okay? Sigma. And then we just take it if it is really the geodesics or not. We have to show that the n dot del n is proportional to n. Okay, that's what we need to show. So n mu. So we want to show. Okay, we want to show. Okay. So since it's known, I mean, if it is geodesic, I mean, if you properly normalize it, you can just, this is equal to 0. So this is a geodesic equation. But if the n mu is not properly normalized, it has to be proportional to n mu. But then that is the geodesic. That means geodesic. Okay. You understand what I mean? Is it okay? So we want to show this one. So if the properly normalized or normalize, so this is a geodesic equation. However, if you're not affinely parameterized, it's just randomly parameterized. This one, if this is a proportional mu, it means the integral curve is geodesic. So let's show that. Okay, and then we have to do one by one. Okay, we have to do one by one. And mu is equal to n dot this one, f g mu nu del mu s. Okay, and then just to use the Leibniz rule to get the answer. So this means that the n dot del f, okay, is equal to f inverse n mu plus del acts on G is the trivial, it's just 0, so del can act on only this one. So that is the, so f and dot this one, and then okay, so that's the second term. The first term is this nabla acts on F. This is the case. Since the rest of the term is proportional to n mu, so you get that. Okay. So this one is scalar quantity. This one is scalar quantity. So therefore, it's already proportional to n mu. So the question is, we have to show the second term is proportional to n mu. Okay. And let's manipulate the second term. Okay, second term is in fact, so n nu, what was that? G mu rho del nu del rho s times f, right? Second term, so I just write down this one is equal to f times n nu g mu rho. And you can just swap the indices because I mean, swap the indices. That's okay. The both. So here it's a derivative, and then if you use the property of the nabla, you can swap the indices. And then so we just manipulate this one is equal to f and nu g mu rho number rho, and this is equal to f inverse of the n mu and nu, sorry, and nu. Okay. So since the g mu nu del nu s f is equal to n and mu, so therefore this guy is equal to, you just multiply inverse matrix, is equal to del nu s is equal to f inverse and then n nu. So that's the case. So you just plug that into here, and then use the Leibniz rule. Use the Leibniz rule. If you use the Leibniz rule, so if first one acts on here, you get that n square g mu rho del rho f inverse. Okay, f inverse of f plus the f and nu g mu rho number rho number rho and nu, okay, like this way. And then since we know that this is null, so this is equal to 0. So this is equal to 0. First term is this is equal to 0. The second term is already, we know that this is proportional to if yeah, so this is equal to, so then this guy is equal to 1/2 g mu rho number rho n square. N square. So that's the case. And then this is indeed proportional to, so this is indeed proportional to n mu. Is n mu. So that is the yeah, so any, okay. Yeah, so I mean, it's hard to explain. I mean, for me, I mean, since n square is equal to 0, does not necessarily mean, del mu n square is equal to 0. It's not necessarily mean. So n square is on sigma n square is equal to 0. But if you change this the different direction, n can, I mean, if you change sigma n to be orthogonal to sigma, so this n square is no longer 0. So therefore, so del mu n is really normal to sigma. But we know that the normal to sigma is proportional to n. So therefore, it should be proportional to n. So that's the logic of the how you define this one. In any case, so n and mu is proportional to n mu. Okay, so this means that the integral curve of this new geodesic vector and mu is the new geodesic. So that's the conclusion. Okay. Anyway, so that's the conclusion. And if you properly normalize the n, so this really this will satisfy. is the geodesic equation will be satisfied. Okay, so that's the case. Anyway, so it's hard to explain this. Anyway, so and square is equal to 0 on the sigma, but once you change this sigma to orthogonal direction, this can be non-zero. This can be non-zero, but it only possible in proportional and mu, because the tangent direction is always n squared is equal to 0. So that's the logic. But it's since it's normal, it's a normal vector is really this n itself, so it's a proportional term. Okay, so that's the case. Okay. So what it means that in fact this n itself is some new it just creates some new geodesic on sigma. So integral curve of this sigma is in fact on integral curve of n is a new geodesic on sigma. So therefore, it's really parameterized by.
It's geodesic on sigma and at the same time geodesic in the whole space.
Yes, even the whole space. No geodesic, yes. Okay, I think it's a good time to take a break. From now on, we will move on to the final Killing horizon. Yeah, let's take a break before that. Let's take a 10 minutes break. Okay. Fine, so let's get started. So let's now define the killing horizon. So killing horizon is that the so it's a no hypersurface. First of all, no hypersurface. Where the where the killing vector is normal to it. That's the definition. Killing horizon is the no hypersurface. So let's look at an example. Let's look at the example. So we know that this, before just going to the detail. So we know, let's see, what's the best example? We can mention that the, okay. So we know short shell. Short shell. And then if you consider ds square is equal to -1 minus 2m over r dt square plus this one inverse dr square plus r square d omega square. Okay. And we know del t is a killing vector. Killing vector, and we know that the del t becomes null at r is equal to 2n. Do you agree with that? Do you agree with that? Del t is a killing vector. That's we know because the matrix is independent of t. Del t becomes null at r equal to 2n because this one is equal to 0. So therefore, g0, 0, gtt equal to 0 at r is equal to 2n. Okay? So therefore, del t is null. Okay. So we can define the event horizon of a short shell as a null hypersurface where the del t, the killing vector c, del t is a normal to it. Okay. So therefore, event horizon at r equal to 2n is killing horizon of del t. Okay, so that's how you define the short shell case. But furthermore, we define so-called surface gravity. Surface gravity is that they are properly normalized C mu, del mu, C nu is in fact equal to a kappa C nu. So this is the So this C is a Killing vector, appropriately normalized. Normalized. Normalized Killing vector. Okay. So this is called surface gravity. So the reason why I did this kind of derivation, is that the at the horizon, at the Killing horizon. So we know that if C is a Killing vector at the null hypersurface, this derivative is proportional to C nu. That we already derived from this derivation. Okay. At this null hypersurface, this quantity, so if you take the derivative, it should be proportional to C nu. And the proportional constant is called surface gravity. Okay? And it's appropriately normalized that the C square should go to equal to -1 when R goes to infinity. So this is a normalization we take. So appropriately normalized is this condition. We have to impose this condition. So here R goes to infinity, asymptotic flat region. It should be time like -1. Okay. So if you look at this, if you look at the Schwarzschild case, this is indeed a case because GTT is in fact 1 minus 2m over R, right? Is equal to minus sign, right? Minus sign. When R goes to infinity, this becomes -1, right? -1. So therefore, the LT is appropriately normalized, the Killing vector in this case. Okay, in this case. So and then this quantity is called the surface gravity. Okay, let's compute this surface gravity of Schwarzschild. And then if you compute this one, I don't know why, I somehow used the Finkelstein, ingoing Finkelstein coordinate in my lecture note, in fact. In my lecture note, to compute Finkelstein, no, I think the conclusion should be same. So let me try. I made a mistake. So here I just use standard coordinate, standard coordinate for Schwarzschild to define the Killing horizon. This is nothing wrong. It's totally fine. We know delta is a Killing vector, and then we know that the delta t becomes the norm at the event horizon, and then which is normal to event horizon, and then yeah. So that's why the event horizon Killing vector of this one, Killing horizon of the LT, and then so therefore what we want is that we can just can we compute CT delta CT? I think yeah. So we should compute this one. Oh sorry. So maybe I should like this one maybe. Okay. CT So this should be something like the most likely what we need to do is the xi, because I mean xi is really in this xt is like 1 0 0 0. So t yeah, t and r and theta phi like this way. So therefore what we have is something like a delta t ct, which is 0, and then t sigma t, yeah, I think that's it, ct, which is ct. Yeah, it's okay. Like this way. Do you understand what I mean? So I just want to try to compute the surface gravity of this one. And this one, if you compute this one, it should be equal to something like this way. And something like this one. Yeah, something like this one. It should be the same. And then once you set the, so at the horizon, at the r is equal to 2m, so this should be equal to 1/4m. Yeah, it should be okay. So it should be 4m. So therefore, this is the copper of Schwarzschild. Surface gravity of 1/, is the Schwarzschild is like this. Yeah, I don't know why I use the Finckenstein. This is totally valid computation. Okay, let's use the Reissner-Nordstrom case. Okay, since I don't want to make a mistake, I will follow the lecture notes.
And later we use this surface gravity for temperature, right?
Oh, so yes. So essentially, as he mentioned, the surface gravity is essentially 1 / temperature with some number. I don't remember. Let me check. So I wrote somewhere interpretation. Okay, 2 pi. The Hawking temperature 2 pi. So later, we will use I think I may made it. Wait, sorry. 2 pi and Hawking temperature. So later, we will see the surface gravity is the 2 pi over the Hawking temperature, but that's the later part of the thermodynamics and so on.
Will we discuss the relation between, what is the relation between surface gravity and temperature?
Yeah, of course, we will discuss. But before then, actually this one, the reason why it's called surface gravity, it has a very, very nice classical interpretation, which I'm going to talk about from now on. So since he asked, so let me, so let's use a Penrose diagram, because I mean it's the kind of, in the case of Schwarzschild, it's something like this one. Anyway, so those are the physical black hole. So so if you just measure at the infinity, so this I0 over I plus and square plus and square minus. So I think it's okay to, there's a past observer and a future observer, right? So this is okay. And you just put some string on it, and you just consider some particle moving. So just put the particle moving on the tangent direction like this. This tangent direction. So there is some string. Okay. And then essentially, so if you just go to F is equal to ma, right? By Newtonian gravity. By Newton, F is equal to ma, and set the m is equal to 1. So the force, force measured at the infinity observer, and the string, I just put some test particle, test massless, okay. It's really close to the here, and it just really moving to this horizon direction, and just see the acceleration of this particle, or whatever. Then the surface gravity is exactly the same as the acceleration, which is measured at infinity. That's I'm going to talk about it. So the reason why it's called surface gravity is the reason. So the really some forces measured at the infinity when you connect the infinite observer and some the things moving along the horizon on the surface of the horizon. So that's the classical interpretation of the surface gravity, which I'm going to derive from now. So this is a classical interpretation, but for more thermodynamic interpretation, it's one of its temperature.
The equation should be different. I think. Should T equals chi over 2 pi.
E? Oh, yes, sorry. You're right.
2 pi times
2 pi TH. Okay. Yes, thank you very much. Okay, you're right. Yeah. Because I mean here is okay. So therefore the temperature is the smaller mass, the mass of black hole is the temperature is higher. Okay. So the smaller black hole is hotter than the smaller black hole is hotter than it is. Yeah, thank you very much. Yeah. Okay, before then, let's talk about the rational Nordstrom surface gravity. Okay, rational Nordstrom case example, rational black hole, and then so this one is ingoing one, so we have something like this one. Okay, like this way without is equal to r minus r plus, like this way. Okay. And then Killing vector here is the delta B is a Killing vector, we consider. So, I mean, in shear case, we can do the same thing. And we know that the Inflation, so this is R and T. So famously, this is what was that? R is equal to 2m, and the B coordinate is something like this way, and then I don't remember the detail, but something like this one, right? B is something like this one, right? And then something like this one. Sorry. So B is something like this one, and U is something like constant, right? As far as I remember, U is something like that. So that's why it's called, anyway. As far as I remember, this is U is constant. No, sorry. Yeah, B is constant. Yeah, B is constant. And this is U, the white line is U is constant. And U is 0 is here. Okay. u is equal to 0 here. You know, right? This intersection will give you light cone of the space-time. So this is a space-time. I think I should have explained this one before maybe, but you know, right? So this is the coordinate, and then yeah, of course, this direction is the delta v. This is delta v. So the killing killing vector is really tangent and also both normal to this event horizon in the case of the short shell. The same thing happened in the rational Armstrong's case, and then Xi is the killing vector because everything is all the metric is independent of B, so therefore one can just compute the surface gravity. Okay, and then this is the so this becomes null. Null when delta equal to 0, which means the R is equal to R plus minus. Okay. R is equal to R plus minus. So therefore, this is the killing horizon. So R is equal to R plus minus is the killing horizon. Of this delta V. Okay. And how to compute the surface gravity? For surface gravity, we can just compute like this way. So the important thing is that this Xi mu, delta mu, Xi mu is equal to, since they are killing vectors, Xi is a killing vector like this way. Like this way. Okay. Do you agree with that? Since we know that the delta mu, Xi mu, this is equal to 0 because of killing. C is a killing equation. So therefore, we can use this one. And this one, to evaluate this one, so one can simply use the following factors. So d of Xi mu and Xi mu is equal to, Xi mu is the inner product is given over there. It's given by d of minus delta r square, which is the minus delta prime r square plus 2 delta r cubed dr. Okay, that's what we get.
Does the C a null vector or not?
I'm sorry?
Xi is null vector or not?
Xi is a null when the at the horizon.
Vector.
Horizon. So this Xi is the B component. So this becomes null only when this delta equals 0, which is a horizon.
So this calculation is only for the horizon.
So this calculation is so far it's a general. So far it's general, but at R is equal to R plus minus, guy is 0, so therefore we just only care about this del prime part, and then here it just become r plus minus r minus plus r square plus minus minus dr. Okay, so that's the case. And we know the C mu is the C mu del mu is this del del v, and C mu the x mu is in fact the dr. Okay, dr. Okay, because once you take this way, you have to get some appropriate number. So C mu, if you contract C mu and C mu, you will get the, well, how do you get that? This one? What was the case? Sorry. Yeah, so this is a correct one at the, since delta equals 0, C mu has to be delta. Yeah, delta equals 0. So therefore, the dual of the vector delta mu should be equal to dr. Okay. That's the case. Sorry, G mu nu C. Sorry. G mu nu C mu is equal to C nu, right? And we know this is the only B part, so therefore GBR is a, yeah. Do you understand what I mean? So GBR is a non-trivial at the horizon, right? At the horizon, delta equal to 0. GBR is the non-trivial thing. So therefore CR is only the R direction. Yeah, and more precisely, this should be 2. It should be 2. Okay. Then, yeah. 2. So I think I made a mistake in the normalization, but in any case, then what we get is that the so therefore, this is equal to C mu over R. Okay. So mu over R. No, R. 2. Sorry. Over R. Okay. It's 2. So therefore, the surface gravity of this plus minus is R plus minus minus R minus plus divided by 2R squared plus minus. So this is the surface gravity of rational non-stone case. Okay, so that's a calculation. One can. For Kerr, things are much more complicated, and then I plan to keep this one. Derivation of this one is just as an exercise for you guys. So I'm not gonna derive. So this is a homework problem for Kerr.
We calculated the surface gravity for Schwarzschild force, right?
Yeah,
And
Schwarzschild.
this is gamma TTT, right? In the first.
Gamma TTT, yes.
But it is 0 for Schwarzschild.
Is it 0 for Schwarzschild?
Yeah, we can just calculate. There should be, they will be the derivative with respect to time, which actually is time dependent.
Most likely you're right. Maybe that's the reason why I need to do the del T del T. maybe. Wait. Maybe you're right. Maybe that's the reason why we have to use Eddington-Finkelstein coordinate. Anyway, if you use the Eddington, anyway, so I can use just Eddington-Finkelstein. This is B, and then everything becomes B and B, and then everything becomes B, 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 and B. And this is correct. This is correct. This is correct. So this is correct. That I know. But for usual coordinate, if I use this one, I'm not sure if I can compute like this. I hope this is the case. Let me think. There must be a way to compute the even structure by using the ordinary way, but I'm not sure. I haven't done it yet. But anyway, so okay, this is the case. And the important thing is that the most important thing is that when extreme case, m is e equal to or q equal to m. Q equal to m, r plus is equal to r minus, right? This is extremal rational North-Star. Okay? Extremal rational North-Star case. And r plus and r minus is equal. So therefore the surface gravity is equal to 0. Always 0. So therefore temperature is 0. So in the extremal black hole, the surface gravity is 0, so which means temperature is 0. Okay, there is no Hawking radiation. The same thing happens even for Kerr black hole. Kerr black hole, we have m is equal to a case is the extreme case. In that case, r plus coincide with r minus. In that case, the surface gravity becomes 0. So therefore, it becomes the Hawking temperature is 0. Okay. That's the case. So let me move on to this classical interpretation of surface gravity. And to do that, I have to do lots of manipulation. But unfortunately, I don't have a time. So GT, maybe you're right. I think. Maybe, sorry, so in the case of maybe, I don't know. Yeah, maybe the reason why I need to use Eddington-Finkelstein is that somehow the calculation is not, you don't get the correct answer for surface gravity. For if you use the normal ordinary one, ordinary Schwarzschild metric, that's the case. Okay. Okay, so then let's talk about the classical interpretations. As I mentioned, so So we just put the particle at the surface at the horizon, and they just consider massless this inelastic the string between infinitely far away observer with the connected infinite far observer and then the something particle on horizon. And we just keep like how to say holding, so that this particle stay at the horizon. And but you have at the infinite observer, you have to use some forces to keep this particle at the horizon instead of moving inside. So that the force is indeed equal to the surface gravity, first surface gravity kappa. That's which I'm going to derive from now. So one thing we have to accept that so since the C is the normal to horizon, so by the how to say, it's called Frobenius theorem. So this is equal to 0. This is normal to horizon. So this is coming from Frobenius theorem. And derivation and the role I have written in appendix B of this lecture note. So I'm not going to go into detail. Let's accept that. Okay. And then so we know that so if you use this property, AB is equal to 0. So since it's a C is a Killing vector, so Killing equation is satisfied. And if you use this, so this notation you know, right? So this totally anti-symmetric notation, and this is the symmetrical notation. You know, right? Hopefully. So this is C, whatever T ABC means that this is the sum of the 1/3 factorial. Sum of pi is the symmetric group, and then signature of pi, and T pi A, pi B, pi C. So this is the total antisymmetric notation for this tensor. So that's the notation. And if you use this Frobenius theorem as a result, and then plug this, use this Killing equation, what you get is this one. Okay, like this way. So this is just a manipulation. I mean, so you just expand it as like this way, and then plug this equation into here, and then just manipulate. You get this one. I mean, it's just a good exercise to do. I don't want to do it on the blackboard, because most likely I will make a mistake, and then even if I make it, it takes a lot of time. So I'm not going to go into detail. And then contracting with del B, what you get is that the what I'm doing that here? Sorry. Oh, I think the lecture note is something stupid. Sorry. So I think it's just a lecture note is written something stupid. I just take the inner product with the del A, del B, like that. That's it. It's -2. Oh, I think I need to change type this typo. So this is just del A. Okay, like this one. I just contract with del A, del B, both sides, and then manipulate right hand side. Okay, so this is equal to minus 2 and CA and then del A, del CB. So just bring this one into, and then this one is del B and CC. Okay. So I use again the notation. Let's see. Okay. So this one is CA dB and also minus CB dA, right? So this part is anti-symmetrization. But here we can use the Killing spin equation to get AB is minus BA, right? Minus BA. So when you use the contract with this one, you use minus BA to contract this guy, okay? And there's over 1/2. There's an over 1/2, so that you get this equation, okay? Do you understand what I mean? Should I write down more precisely? No, I mean this kind of stuff. It takes a lot of time to write. Anyway, so the CAB, del B, CC, and then minus C, what was that? B D del A, CC. So that's so inside here, right? And then you have a del A, CB, right? Well, if you just use this one times this one, you get the half of this one, okay? But if you contract with this guy and this guy, you use the Killing spin equation to swap A and B. At the cost, you get the minus sign, and so you get the minus times minus, you get the plus, okay? You get the half of this one. So this is okay. Anyway, so this kind of stuff you have to do on your own. You're already master student and so on, and so I think you should be able to do. Fine. Then oh my goodness, this lecture note has a lot of typos. Sorry about it. So this one is minus 2 and a kappa of CB, right? So the first one is the kappa of CB and delta B and CC. So therefore this, and again you have a minus 2 kappa square CC. Okay, so that's what you get. Do you agree with that? So my lecture note is full of typo around this point. Sorry about it. Okay, full of typo. So therefore, so from here, so the kappa square, from here kappa square is equal to minus 1/2 del A CB del A CB. Okay, so you just compare between these two. Fine.
This is formula for surface gravity, right?
Yes, yes, yes.
And in order to calculate, we should do calculation in coordinating the Finkelstein coordinates.
I mean, yes. I think so. But from now, I will derive from this kappa is the acceleration, really acceleration. If you use the definition, you don't need to use the Finkelstein whatever coordinate. The ordinary coordinate will be okay. I will show that. Yeah, so this is another way to derive it. But if you use this one, most likely even the ordinary coordinate should be okay. Because this, if you use this one is t, c is t, that can be like r and so on, right? Most likely. This will give you non-trivial, right? Most likely this will give you non-trivial one. Because I mean the gamma 0 r 0 is non-trivial. Is non-trivial. And this is also give you non-trivial. And if you compute and then take a square root, even ordinary metric should be okay. Give you correct answer. Do you understand what I mean? Yeah. So I think if you use this one, no need to use the Finkelstein, Eddington Finkelstein. Yeah, most likely yes. This yeah. Okay. And then what I'm going to do is the giving a physical interpretation copper. To do that again we will do some kind of manipulation. C, A, B, C, C. So we know this is equal to 0 at the horizon. And C, okay, and this is just manipulation. This is really tedious manipulation. One can do delta B, CC, delta B, CC. So this is the case. Of course, I used the Killing-Spin equation to this one, to get this one, times 3, sorry, times 3. So this is just a manipulation of this antisymmetric tensor with this Killing equation, and then you get this one. And we know that at the horizon, left-hand side is equal to 0. At the horizon, this is equal to 0 at the horizon. Yeah, so this is only true. This is only true for at the horizon, Killing horizon. Okay, Killing horizon. So the left hand side is equal to 0. And now, so we already noticed that this part is the same as this part. Okay, this part is the same as this part. This part. So left hand side is equal to 0 at the horizon. And this part is the, what was that? Is equal to minus 2 kappa square. Okay, 2 kappa square. And you just compare. So therefore, kappa square is equal to CA del B CC CB del A CC divided by and then CA. Okay, do you agree with that? At the horizon. Yeah, at the horizon, sorry. Kappa square is a limit. R goes to R horizon. Okay. And then nothing against to swap this guy to here and this guy to here, so therefore one can just write down B here and A here. It's okay, right? There's nothing against you. Okay? Fine. So now what's really interesting is half of this guy. So half of this guy. So if you multiply it against CA like this way, so then this guy is will give you kappa, right? So that's we know. So the kappa square is this times this. The same thing now. So this is kappa, this is kappa. Okay? Do you agree with that? So that's the case. So okay, now we are going to evaluate this quantity, CB, del B, CC, this is CA and CA. And we call this one is SC. And hopefully I'm fine with that.
Why multiply in the denominator like say I? In the denominator you multiply.
Oh, this one?
Yes.
No, I think the square root. Sorry. Yeah, I think 1/2. 1/2 and 1/2. This is democratic. Democratic. Okay. And most likely I need to put the minus sign at some point. But anyway, so okay, so that's a democratic. Okay, a way to do that. So this is 1/2. 1/2. Okay. So that's the case. So to consider this quantity, hopefully it's okay. No, it should be okay. Yeah, somehow I make a mistake in the, okay, maybe I will put the minus sign here. It's okay, right? So even if you put the minus sign, if you multiply them together, you get the plus sign, so it should be okay. Yeah, I think this is the, yeah, minus sign, so okay, so this is okay. Okay, let's manipulate this one, this quantity. So this is in fact equal to as follows. So consider the u. So consider u is the properly normalized. So this is CA square root and then CA like this way. So normalize the unit vector so that the US UA. Okay. Somehow I made a mistake in somewhere in the sign. Somewhere in the sign, I don't know where. Okay, I think seems like I need a minus sign somehow. Okay, anyway, so I don't know. Somehow I made a mistake in sign. I don't know where, to be honest. Can anybody detect that? Okay, so up to sign, oh, it's okay. Up to sign, so this is equal to 1 or minus 1. I just want to have this is minus sign. It's just appropriate normalized the appropriate normalized Killing vector minus sign. So therefore, I just want to have a minus sign. Minus sign, minus sign, minus sign here. I don't know where I make a mistake in this computation. Okay, let's accept this one. I would next time I will find a way I made a mistake in sign, and then move on. So then I just want to have acceleration. Acceleration of this object is really UA, the A, UB. So this is the acceleration of this observer. So okay, observer, and we just want to consider this U is the really observer at the horizon, okay, at the horizon. So U is the observer, or some particle at the horizon, and the acceleration is given by this object. This object, and this is equal to CA over B del X CB over del B. B is the square root minus CA, okay? And then this is given by 1 over B square, CA del A. And then del A 1 over B. Okay, so that's the case. And if you use the property of the Killing vector, so this is in fact equal to BA and the inverse, right? So therefore this is equal to del B log of B, okay? Log of B, so that's what you get from this from this.
The minus sign in the denominator was the problem, right?
Yeah.
And I think this is because the square of psi is -1
Mhm.
for the time of
Yeah, yeah, yeah.
So in order to put it under the square, we should put minus in front.
Minus in front.
That's my reason.
I think so. So.
For example, when you calculate the chi-square,
Uh-huh.
like definition, the first part in the numerator gives kappa times psi z, c.
Which one?
First, no,
This one?
here, but first element, element on the numerator gives you kappa times psi c.
Yes, yes.
And the second one is also kappa times psi c.
Yes, yes.
Then there is a psi squared in the numerator and psi squared in the denominator.
Yes,
This
yes,
this
yes.
is true. And the psi squared is -1.
Yes.
So in order to put in the square root, so you should need -1.
Is it true?
The problem is the minus inside the square root, right?
Yes, yes, yes.
So
But sorry, so this one is equal to kappa CC, right?
yes.
And this is kappa CC, right?
Right.
And this is kappa square C square, right?
They can cancel.
Yeah.
You can get kappa square. I mean the whole expression is true.
Yeah.
So the reason of why you have minus in the denominator is
Yeah.
that in order to put it inside the square root, you
That's
should
correct.
have a positive value.
Ah, I
And
see.
psi squared is
Ah, I see.
-1.
I see. I see. Okay. Okay. Maybe that's the case. Okay. Anyway, so. Okay. Fine. And where are we? Anyway, so if you compute this one, you get this one. If you compute this one, and this is exactly equal to this guy. So this, if you just compute this one, you get this one. This is AB is equal to this one. Yeah. And the acceleration at the infinity is just you have to appropriately normalize the infinity. So limiting value is the acceleration measured at the infinity is related by acceleration at this point. A is in fact so AC, and square root. And V is exactly the normalization we will take. Normalization we will take. This is the acceleration of this. So therefore, once you find, so this is in fact equal to this guy. Okay, this guy. And then, is it the case? Am I correct? V is this one. It should be okay. Simplify to this one. It should be okay, right? Am I correct? So therefore, in any case, the acceleration is the measured at infinity. Measured at infinity with infinite strength will give you the this is kappa. Is kappa. That's the case. That's the one thing one can do. That's a physical interpretation of this surface gravity. I hope I don't make any mistake. I hope I don't make any mistake. Sorry, maybe I don't know. I'm not. To be honest, I'm not confident enough. Let me think. Am I correct here? So now I just got confused. It seems like it's not correctly normalized. Let me do the computation. Okay. I think it should be easy. Okay, sorry about it. So the log of square root. Okay, let me help me. Could you help me? And if you take the del b, so you get the minus CA, right? And then del b acts on this one, right? Do you agree with me? So far it's okay, right? And how does this act on it? It's just I mean, that's so stupid. And so this one is give you minus CX, CA del B, CA. Is it the case? Is it the case? It should be the case, right? Am I wrong? You guys are good at this kind of stuff, right? F of x square ddx. How do you do this kind of stuff? What are you doing? No.
There's also factor 2.
Huh?
There's also factor 2, maybe.
Yeah. So do we need a factor of 2 here?
Yes, because we do derivative of a square.
Okay.
I mean, there are 2 parts.
Oh, factor of 2. Factor of 2. 2. Factor of 2. Okay. Factor of 2. This should be okay, right? This should be okay, right? Okay. Then the first term is explained. The second term is how to get it. Okay, so it should be okay. It's okay. It's a factor of 2. It's the same term, right? It should be same term. Yeah. Yeah, it should be same time. So this is okay. So far this is okay. And this is equal to this guy. And the factor of 2 is somehow strange, but here to connect that one, what we need to do is what? So AC, so this is the okay. So then the factor of 2 square root is missing.
But there shouldn't be factor of 2.
It should be factor of 2.
Shouldn't. When you differentiate the square root, it's 1/2.
But there's square root 2, so you get 1/2
Yes.
to cancel.
Yes.
To cancel. So it should be okay.
Yes,
It should be okay, right? It should be okay, right? And then this is not AC. This is the not AC. That's a point, I guess. Okay. And if you take AC square, what you get? So let's call this is AB, and the AB, and take a square root will give you minus CA times this one, right? That will be CA, and then CA, that will be CA. Okay, so that's the case. And take a square root. Square, right? Okay. Square root this one. And then the more need. And this is equal to kappa times 1 over this one. Minus CA and XCA. Okay, this should be okay. 1/2. Okay, so then the multiply this one, you get this relation. Okay. Okay, so this okay. So this is equal to kappa. And then it should be okay. No, I'm fine. Okay, I'm fine with that. Okay, thank you very much. Anyway, so this is equal to kappa. Okay. Sorry about it. So important thing is that this is measured at the from infinity, because I mean here it's important part is that the so this A infinity is equal to B times A. And this A is in fact divergent quantity. In Schwarzschild case, A is equal to 1 over D, 1 over 2D log of 1 minus 2m over R. Okay, so that's the case. 2m over R. And then this is equal to m over R squared, 1 minus 2m over R dr. And this is like divergent quantity it's divergent quantity at the R is equal to 2m. So A itself is divergent quantity, but the B is becomes 0. B is in fact 2 times 2m over R. So B is in the Schwarzschild case. B is equal to 1 minus 2m over R. Okay. So therefore, this cancel with this one. When R is equal to 2m, you get the correct value of the surface gravity A infinity. Okay. Do you understand what I meant? So A infinity is the really m over R squared when R is equal to 2m. But B is becomes 0. A is divergent. Okay. So this A itself is a local measurement acceleration. So therefore, it's the if you just look at the place at the Schwarzschild black hole, and then they just measure at the very, very tiny length of the observer around here, and they just connect between strings. This string will be, how to say? Will be destroyed because of infinite acceleration. Okay, but you have to bring this string to the infinity to make it finite, because of to do that you have to multiply this factor. Okay. You really need to multiply this factor. Okay, so that's the case. So that's the classical interpretation of surface gravity. Okay. Okay, let's stop here. Yes.
So minus 1 inside the square root is because originally there should be minus 1 in the denominator. So looking at this, second, so minus 2 kappa squared times this equals, because this part is 0, so kappa squared equals.
Oh, yeah, you're right,
yeah.
you're right.
So
No,
minus
it's okay.
Oh.
Right? Okay. Oh yeah.